Hello and welcome to lesson 3 in our study of differential equations 2. So, in this lesson, we'll be talking about the Laplace of derivatives, and we will also learn how to use the Laplace transform to solve IVP problems in differential equations. So, I hope you've enjoyed the first two lessons, and by now you've revised your Laplace transforms and your inverse Laplace transforms. Okay, so to solve a differential equation by Laplace transforms, we go through 4 distinct stages. Okay, and these stages are listed below here. So the first thing we do is that we rewrite the equations in terms of Laplace transforms. Then after that, we insert the given initial conditions. Then after that, we rearrange the equation algebraically to give the transform of the solution. Then the last step is we determine the inverse transform to obtain the particular solution. So you could see that here we find inverse transform, here we find the Laplace transform. So that's the reason why, to understand this course, you should really know your Laplace and your inverse Laplace. Okay, so that was what we did in the first two videos. If you haven't watched them, you can go back to watch them before watching this one to help you understand things easily. So now, when you have a differential equation of this form, for instance, ay prime prime plus by prime plus cy equals f of t, and we have, let's say, initial conditions at y of 0 equals say 1 and y prime of 0 equals say 0. So when you have a differential equation of this form and you want to solve it using the Laplace transform, okay, you have to first transform this differential equation here in terms of Laplace. So that means you have to find the Laplace of y prime prime, the Laplace of y prime, the Laplace of y, and after that you find the Laplace of the function here. So that means we have to learn how to find the Laplace of derivatives, because if you don't know how to find the Laplace of derivatives, then you can't find the Laplace of this y prime prime, y prime and y. Okay, so we have to learn how to find the Laplace transform of derivatives. So this y, for instance, the Laplace of this y is equal to a certain big Y of s. Okay, so for instance, if it was x, then the Laplace of x will be a certain big S of x. Okay, so that's it. Then the Laplace of y prime is given by what we have here. So for example, it was Laplace of x prime, so that have been this. Okay, and the Laplace of y prime prime is this, and the Laplace of y prime 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 is that. And even in this lesson or in this course, it's very likely that we'll be ending at the second order. Okay, so you have to know these. Okay, actually they have ways through which they were derived. You can go and look at them, but aside that, in differential equations no one will ask you to prove them, so you have to know these ones. Okay, so generally we have this to be the general. So the Laplace of y of k is equal to what you can see here. So from this you can construct the Laplace of this, the Laplace of this, or what have you. Okay, so you have to know how to find the Laplace of the derivatives. You just have to know them off head, because they are going to help you a lot. Okay. Alright, so now that we know how to find the Laplace of functions, the inverse Laplace, and we've just learned how to find Laplace transform of derivatives, then that means we can put all these three together and use them to solve differential equations, right, with initial conditions using the Laplace transform. So we are going to take two examples, okay? So let's start off with example 1. So example 1 says that we have to solve this differential equation here with these initial conditions using Laplace transforms, okay? So this s dot dot minus s dot minus 2s equals 0 is the same as s prime prime minus s prime minus 2s equals 0, okay? So this is the same as maybe something like so something like this, okay? So we have to find the solution to this differential equation, which is x of t. So from the methods you've learned earlier from differential equations 1, you can use some of them to solve this. For instance, with this you can find a characteristic equation, and from then you can get your solution, okay? But I'll be using Laplace to solve this. So the first thing that we do, so do you remember the 4 stages we talked about? So you first rewrite the equations in terms of Laplace transforms. So that means the first thing that we have to do is to find Laplace transforms of the derivatives and every function there is. So the Laplace of x is this, Laplace of x prime is that, and the Laplace of x prime prime is this, okay? And the Laplace of 0 is 0, because Laplace of a is equal to a over s. So that means Laplace of 0 will be equal to 0 over s, which is the same as 0, okay? So now that we have the Laplace of everything, then we can put them inside this equation to transform it. So we've just made a substitution. So that means these are x prime prime, these are x prime, these are x, this Laplace of 0, which is 0, okay? So when we have this, then we can work on what we have here. So negative times this gives us negative, then negative times negative gives us positive. So that gives us this equation we have here. Then the steps, the second one says we insert our initial conditions, right? So that means we have to insert our initial conditions, and it is x of 0 equals 1 and x prime of 0 equals 0. That means wherever you find x of 0, we put 1 there. X prime of 0, we put 0 there. So here we put 1 here. So we make that substitution, to give us what we have here. Okay. Alright, so after we are done, then we try to bring the ones containing this, right, together. So when we do that, we have this equation here. And after that, we maintain that on the left hand side, and we send anything remaining to the right hand side. And that gives us this. So here we've just factorized this out. Okay. So when we are done, we made that a subject. So making that a subject is going to give us s minus 1 over s squared minus x minus 2. So we've been able to arrange this algebraically. Now we have this equation. Okay, so the next thing for us to do is to find the Laplace inverse of this function here. And if you're able to find the Laplace inverse of that, that gives us the solution to the differential equation. So we have to find the Laplace inverse of that. Alright, so we take the particular function and we use partial fractions on it. Okay, so s squared minus x minus 2 can be written as s minus 2 then times s plus 1. That's the denominator. Okay, so that means that instead of having s minus 1 over s squared minus x minus 2, we can have this. Then when we have this, we resolve it into partial fractions. So we have this here will be equal to a over s minus 2, then plus b over s plus 1. So you should know how this is done from our first lesson. So here we have to find for a and b. So they have a common denominator, which is x minus 2 times x plus 1. So that means we have s minus 1 will be equal to a times s plus 1, right? Then b times s minus 2. So when x is equal to 2, that means we get 2 minus 1 will be equal to a times 2 plus 1, then plus b times 2 minus 2. Then this part is 0. So that means the b goes away. Then we have 1 will be equal to 3a. And solving for a will give us 1 over 3. So then we have a is left with b. So when x is equal to negative 1, then we have negative 1 minus 1 will be equal to a times negative 1 plus 1. This gives us 0. Then b times negative 1 minus 3. So this gives us negative 2 equals negative 3b. Then when you find for b, you get b equals 2 over 3. So now we have the value for b and a. So we can put them inside this. Okay. So inside this. So doing that will give us 1 over 3 x minus 2 plus 2 over 3 x plus 1. So now we can easily find the Laplace inverse of this. Okay, so we have the Laplace inverse of 1 over 3 x minus 2 plus 2 over 3 x plus 1. And since the Laplace operator and the inverse Laplace operator are both linear, we can write this in this form. So it being linear means like the Laplace inverse of f of t plus g of t is the same as the Laplace inverse of f of t plus the Laplace inverse of g of t. So writing in that form gives us this. Then remember we can bring our constants out, so we bring them out when we have this. Then the next thing for us to do is to find the Laplace inverse of 1 over s minus 2, and this is this. Then Laplace inverse of 1 over s plus 1, and that is this. Okay, because when you find the Laplace inverse of the exponential function to give you something of this form. So that means when you have something of this form and you are going back, you always have something of the exponential form. Okay, so now since this is e2t, this is e minus t, then we can write it and we will get this. Alright, so hence the solution of our differential equation is s of t equals whatever we have here, and that happens to be the solution. So we've been able to use the Laplace transform to solve differential equations with initial value conditions. I hope you got it. If you didn't get anything, you can pause the video and rewatch it, okay? But let's take a second example, which happens to be more complicated than the first one, but it's very simple when you follow. So it says solve this differential equation with these initial conditions by Laplace transforms. Okay, so this is our differential equation. S prime prime plus x equals sine 2t. So the first thing we have to do is to make transformations, right? Using the Laplace transform. So we have to find the Laplace transforms of the derivatives and that's of the function. So the Laplace transform of x prime prime is this. That of x prime is this. And that of s is this. Then we also have to find the Laplace transform of sine 2t. So the Laplace transform of sine 2t is 2 over s squared plus 4. By now, you should know how we did that, because in our first video, we showed the reason why the Laplace of sine at is giving us a over s squared plus a squared. So now we have the Laplace transform of s prime prime, that's of x, and that's of sine 2t. So we have to make substitution. So making substitution gives us this. Okay, where this here is our s prime prime, this here is our x, and this here is our sine 2t. So after we are done, then we put in the initial conditions. So x of 0 equals 2 and x prime of 0 equals 1. So wherever you find x of 0, we put 2 there. Where you find s prime of 0, we put 1 there. Sorry. We put 1 there. Alright. Then we can rearrange the equation such that all the ones containing x of s, okay, are at one side, and we send the others to the right hand side. So that will give us this equation here. Then after that, we bring this out, and that gives us s squared plus 1 equals whatever we have here. So we try to make that the subject. So we divide through by s squared plus 1. And that gives us this. Okay. So when we have this function, we would like to add the two together. So we find LCM, which happens to be s squared plus 4 times s squared plus 1. So we just work around that, and that gives us this. Okay, so when you do this, you also get this. I mean, this is just algebraic computation, so you can just look through and do that. And that finally gives us this. So that means when you try to add these two together, you will get this. Okay, so now we have this thing here. So to get the solution to our differential equation, we have to find the Laplace inverse of this. So we resolve this into partial fractions and we solve that. Okay, so since we have quadratic terms here, it will take this form. So es plus b over s squared plus 4 and cs plus d over s squared plus 1. So by now you should learn how to resolve functions into partial fractions, okay? So, since you have a common LCM, then we multiply as plus b through by s squared plus 1 and cs plus d through by s squared plus 4. So we're doing that gives us this equals this and this, right? So we just have to multiply them through. So as times s squared is this, as plus 1 is this, so this and this is this, this and this. So we just go through. It's very simple. Then after we are done to get this, we try to group them. Okay, so then we have as cubed and plus c s cubed, right? So that will give us a plus c s cubed. Then we have b s squared plus d s squared, so that gives us b plus d s squared. Then we have as plus 4cs, so we have this in b plus 4d. So when we get here, then what we do is that we compare the coefficients. Okay, so by method of comparing coefficients, as plus c, where's my red a? As plus c will be equal to 2, that's equation 1. B plus D will be equal to 1, that's equation 2. A plus 4C will be equal to 8, that's equation 3. And B plus 4D will be equal to 6, that's equation 4. So now we have systems of linear equations. So you go back to your numerical analysis or your linear algebra and you solve this system of equations. So when you do that, you are going to get A to be 0, B to be negative 2 on 3, C to be 2, and D to be 5 over 3. Okay. So now you can make substitution. So wherever you find, you can make substitution into this. You place your A, B, C, and your D's. So doing that is going to give us what we have here. Okay. Then now we have to find the Laplace inverse of that to get the solution. So since the Laplace inverse is a linear operator, we can rewrite this into this form, right? So that we can bring the constant out. So you get negative 1 over 3 Laplace inverse of 2 over s squared plus 4. This, and we get that, okay. But so you have to find the Laplace inverse of, I think there's minus 1 over 3 here. Laplace inverse of. So the Laplace inverse of 2 over s squared plus 4 is sine 2t. You should know all this by now. Laplace inverse of 1 over s squared plus 1 is sine t. And Laplace inverse of s over s squared plus 1 is cos t. That means you just have to make those substitutions. Okay, so making that will give us s of t, that's the solution, will be equal to negative 1 over 3 sine 2t plus 2 cos t, then plus 5 over 3 sine t. Okay, then you can try to rewrite that. So you get s of t will be equal to 2 cos t plus 5 over 3 sine t minus 1 over 3 sine 2t. Okay, and that happens to be the solution to the differential equation. So if you didn't get anything, you can always rewatch the video or go through it, and that is going to help you to understand things better. Okay, so the next video is going to be on Heaviside functions, where we talk about the unit step up, step down, and what have you. Okay, so there's a trial question here to test your understanding of what you've learned. You can try to use the concept to solve this differential equation here: y prime prime minus 10y prime plus 9y equals 5t, with y of 0 equals negative 1 and y prime of 0 equals negative 2, and y of t So when you're able to solve it correctly, your solution y of t should be this. Okay, so try and solve this question after watching the video to see whether you understood things or not. So thank you very much for watching this video. Don't forget to subscribe if you haven't, so that you easily be notified of future videos, and don't forget to like the video if it helps you. So thank you very much, and see you in the lesson 4.